Hey everyone, I have a couple of word problems that I'd like you to go through with me. This will help you learn some more about attacking word problems, how to translate them and solve them. These two that we're going to look at are especially important because they involve a very important formula. This is a formula I want you to memorize. It is distance. Hold on. Distance equals rate times time. Now, rate is just a fancy word for speed, and that's a very powerful formula when you're dealing with word problems that involve speed and time and distance. It helps us translate the words into equations a little quicker. Some word problems we don't have the equation at all, and we have to read the problem and create the equation from the words. But here, this word problem involves a formula, and that makes it a tiny bit easier because we don't have to invent the equation. So I want to give you some tools as well for solving word problems. I'm going to start a list here, and I encourage you to write this list down somewhere and keep adding to it. But one tool is to use formulas. Now, of course, not every word problem is going to allow you to use a formula. Sometimes the words you have to kind of just create the equation to make it work. But that's an important tool. I'm going to add a couple more others as well. But let's read this problem together and see if we can understand what's going on. After robbing a bank, a robber runs off at 7 miles per hour. 15 minutes later, the constable pursues the robber on a bike at 14 miles per hour. How long in hours does it take the constable to catch up to the robber? All right, one of our tools that we've talked about before is look for the unknown. Okay, so I'm seeing that here in a question that there's something involving time. So that's one of our tools, is try to figure out what the unknown is. Now, sometimes there's more than one unknown, but that at least gets us started. We're trying to find time. Another tool that we've used before is start collecting all the data. Now I see different things in here that's data about speed. The robber's running 7 miles per hour. The bike is going 14 miles per hour. And often we will list that information. So I'm using the tools. Look for the unknowns, list the information. Now I'm going to show you a different way to list the information in a moment. But here's another tool. Not always can you use this, but when you can, it will help you understand the problem. Draw pictures. So for instance, we got a bank. And doesn't look like much of a bank, but there we go. The robber steals money from the bank and he takes off running. Now, the constable hasn't even started yet. So the robber is running for a while. And how long has he been running? We don't know. Oh, wait, it says 15. Has the robber been running for 15 minutes? True or false? The 15 is not how long someone has been running. It says 15 minutes after or later. So the robber began running, the cop began bicycling 15 minutes later. That doesn't tell me how much time the policeman has been riding his bike. It doesn't tell me how much time the robber has been running. So the 15 minutes is not how long either one of them have been going. That would be false. The time is definitely unknown. Okay, now there's another concern here. So the constable or the cop hasn't started running yet or biking. When he does get on the bike, the robber already has a 15-minute head start. And so when the constable is biking, the robber is still running. But the constable is biking faster than the robber can run. And eventually, the constable is going to catch up to the robber catch him, and arrest him. So by drawing that picture, it helped me understand a few things. The times are different. The robber has been running for a while, and the policeman didn't even start until 15 minutes later. So he has been biking less time. All right. So that is a tool that I find, and I think will help you as well, is drawing pictures. Here's another tool. Make a chart. Now, a chart is not a tool you can use in every single word problem, but it is a good tool to help you organize when word problems have lots of pieces. And this problem has lots of pieces. There's a robber, and he has a distance that he ran, a time that he ran, and a speed he ran. So the robber has a distance, rate, and time. The cop also has a distance, rate, and time. So there's like 6 different pieces to keep track of. Here's where a chart can really help us. So let me illustrate the chart strategy here. Let's break down all those pieces. Going to make a little chart to organize all the different thoughts. We have a robber, and we have the cop. Now, both of them have a distance that they went. Both of them have speed they went, and both have a time they went. And when we do the chart this way, it helps us organize all the information that we have. Before, we used to list all our number facts, but now we can list them right in the chart. The robber has a speed of 7 miles per hour. The cop has a speed of 14 miles per hour. Okay, so that helps us organize a little bit. Now, let's address the time issue. The robber is running, and remember, he was running longer than the cop. So the cop also rode his bike for a certain amount of time. Now, this would be an error because I'm using the time variable t, one variable t, for both the robber and the cop. But the robber and the cop are not moving for the same length of time. They have different times. So because the cop started 15 minutes later, his time is not the same as the robber who was running longer. So we have 2 different times, time 1 and time 2. Now, whenever possible, we want to avoid having many variables. This means I have 2 unknowns, time 1 and time 2. That's going to make it complicated. I don't want to make it complicated here. So what I want to do is try to figure out one variable, t, for both the robber and the cop. And so I'm going to take this out. And so what I'm saying in the chart is t equals the time of the robber's running. We used to do t and explain the variable time that the robber runs. That explains the variable, how we used to do it. And I always want you to explain the variable. But because we're putting t as our variable, and if you want, you can call it x. It doesn't matter what variable you call it, but I'm going to call it t. Since it's in the chart here, t is for time, and t is for the robber, so I know that it is the time that the robber was running. So we don't need to explain the variable the way we've been doing it with a sentence or a phrase like that. So the chart has taken care of our first step. It explains the variable. Okay, next. So the robber has a time. There's a time here. Now we got to figure out the time for the policeman. The policeman starts 15 minutes later, and he's trying to catch up to this guy, and eventually he catches up. And when he catches up, he captures him and arrests him. How long was the time for the police officer? Okay, we don't know what that time is because it depends on the robber. If the robber was running for a while and the policeman started 15 minutes after that, we've got to know how long the robber was running to figure out how long the police officer was biking. Now, we don't know what the time for the cop is, but because it depends on the robber, we can get a formula. Now, this is a second unknown. This problem has a hidden unknown in that it doesn't say much to us about the time that the cop was riding his bike. However, I want to show you another tool. Plug in simple numbers. Now, the strategy of plugging in simple numbers is not to figure out the answer. The strategy is to help you figure out the math for the formula. That's supposed to be math. I don't know what the formula is. And sometimes you can be stuck with that. But if you plug in some simple numbers, it will help you figure out the math. Now, I don't know the answer, so I'm just going to randomly pick something to get me started. I'm going to pretend that the robber was running for 45 minutes. I just picked an easy number. You could say 60 minutes. You could say, 2 hours, whatever. Now, because I'm assuming that the robber was going 45 minutes, what do I know about the policeman? How long was the cop riding his bike? Well, it says that he started 15 minutes later. Okay, so the robber's running 45 minutes, the cop ran 15 minutes later. That means he was going for 30 minutes. So once you pick a simple number, often the simple numbers help you see simple outcomes. Now, that's not the answer, but it does help me see the math. What is the math for the police officer? Well, we have to take 15 minutes off of the robber's time. So if the robber's time is T, then the policeman's time is T minus 15 minutes. We just figured out the formula. So we have two unknowns, the robber's time and the cop's time, and we can make the cop's time with this formula. Now don't write that in yet because there's another little hiccup here. The hiccup is, this is in minutes. The cop's time is 15 minutes less. And the speed is in hours. Miles per hour. So if we do the 15, which is in minutes, and the 14, which is in hours, it's going to totally mess up our outcomes because they don't agree. We have to make the whole problem agree. So it's got to be all about hours or all about minutes. And it's going to be easier to make this about hours. So we need to change the 15 minutes into how many hours that is. So 15 minutes, if you divide it by 60, you get 15 goes into that 1/4. So it's 1/4 of an hour. If you need to, the fraction is better if you can see that. If you divide it and get a decimal, you get 0.25 hours. And the decimal actually makes the algebra a little harder. I don't recommend the decimal, but some people just need them instead of fractions. But I encourage you to always convert to fractions when possible. So, what's my formula for the policeman's time? He takes the robber's time, and he started a quarter of an hour later. So I'm going to subtract the quarter of an hour. Now I've figured out 4 parts of the 6 pieces in this problem. And I got one more part that I could figure out. Distance equals rate times time. But before I do that, so I have to figure out distance. But got to figure out one other thing. Where is this all going? I'm trying to find time. How long? That's my unknown, the time. And I need equations. Is there any equation in this problem that will help us? Well, when does the cop catch the police officer? I said that wrong. When does the cop catch the robber? Well, he has to catch up to the robber to catch him. That means they've gone the same distance. So their distance is the same. The distance that the cop went is the same distance that the robber went. That's my equation right there. You don't have to write this down, but the distance of the robber equals the distance of the cop. Now, I don't know what the distance is, but I do know a formula. Distance equals rate times time. So the robber's distance is a rate of 7 times his time. The policeman's distance is his rate of 14 times his time. There we go. Because the cop caught up to him, his distance is the same as the robber, which means the distance equation for the robber equals the distance equation of the cop, and I have an equation now that I can solve. So we want to get t by itself. So let's get rid of parentheses. I'm going to distribute 14 times that one, 14 times that one. So I get 14t minus 14 times 1 over 4. So I get 14 over 1 times 1 over 4, which is 14 over 4. Now, if you really hate fractions, you can clear the fraction, times everything by 4, and you'll kill that one fraction. But for me, I'm thinking that extra step, it's not worth it to get rid of just one fraction. If there was more than one, I might do it. But I think with just one fraction, I'm going to live with it. And I want to get t by itself. So I'm going to minus 14t, because I have t's on both sides. That's making it hard to solve. So I'm getting rid of the 14t on the right side. Now 14t is negative. 7 minus 14t is negative 7t. Positive 7, take away 14 is negative 7, equals negative 14 over 4. Okay, almost done. I want to get rid of the negative 7. I'm going to times by the reciprocal, negative 1 over 7 on both sides. Now you can divide by 7, but you have to take the fraction negative 14 over 4 and divide it by 7. So if you did it that way, I'm going to draw it out. Negative 7 over t. And you have to divide both sides. Divide negative 7, divide negative 7. So over here you have to do fraction division, which is totally fine if you like that. But for me, I like the reciprocal way better. It makes it a little less writing, and it makes a multiply, which is a little easier. So the negative 7 times negative 1 over 7, the negative times the negative is positive, and the 7's cancel, and I get t by itself. On the other side, negative times negative is a positive, and 7 on the bottom cancels with 14 on the top, and I get 2. So I have 2 over 4, which is 1/2. All right, we solved the equation. We got an answer here. What does 1/2 mean? Okay, 1/2 is t. It's the time. Is it the time for the robber or the policeman? That is half an hour that the robber was running. We found the answer for how long the robber was running. Now, How long does it take the constable to catch the robber? So technically I have not answered the question yet, because the question is not about how long the robber was running, but how long the constable was running. So we have to take a quarter off of that. Half an hour minus a quarter hour, that means 1/2 minus 1/4 equals 1/4 hour that the cop was biking. If you put that back into minutes, the robber was running 30 minutes and the cop was biking for 15 minutes and he caught up. There you go. That's an example of using a tool for the chart. But I've actually illustrated 4 tools that you can often use in word problems. Like look for formulas that might work, or draw pictures, make a chart, or plug in. I'm going to do another problem that illustrates the chart here. Okay, here's another example. 2 cyclists. They're 60 miles apart. They start riding towards each other at the same time. That's important. One cycle is, there's an equals. Notice how I'm grabbing keywords here. One cycles. Oh, that's poor grammar. It should say one cyclist. One cyclist is 1.5 times faster than the other. Oh boy, the grammar in there is really bad. I left out some words or typos or something. So one cyclist is 5 times faster, it needs to say that, than the other. If they meet 2 hours later, what is the speed in miles per hour of the fastest cyclist? Okay, now right away, hopefully you're connecting here. This problem says something about distance, rate, and time. So when we think about our tools, oh, this could be a formula problem. Distance, rate, time. And when you have distance, rate, time, the chart is another tool that can help a lot when there's a lot of pieces. The ones we did in class, there's only one distance, one rate, and one time. Those didn't really need a chart, but here we have 2 different cyclists. So this is making it a little bit more complex. So I'm going to try to organize it all with a chart. I have a distance, a rate, and a time for the fastest and the slowest. Now, you could do fast and slow as your 2 cyclists, but slower. But I'm going to use the words in the problem. Now, the words in the problem are a little obscure, but I'm translating English into algebra. Now, as far as the English goes, this one should say cyclist, and this one should say faster. Now, the words that we have to translate represented in English are one and the other. So because that word one, cyclist, is connected by the word is. Is a great word in a sentence for algebra because it means equals. So 1 equals 1.5 times faster. Oh, times is multiplying. 1.5 times the other. That's giving me an equation there. So it's a pseudo equation, but it's talking about their speed. And I'm going to need that later. So let's put that note up a little higher. 1, quote, equals 1.5 times, quote, other. Now, if it's clear to you which one is which, you don't have to use the word one and the word other. You could use the faster. And one is the faster cyclist. Other is the slower cyclist. So we take 1.5 times the slower speed to get the faster speed. So the 1 equals 1.5 times the slower speed. But we'll kind of keep piecing this together here. Another tool I want to pull out is to help me understand the problem. Now, you may not need it. You may be able to fill out the chart and write the equation and good to go. But if you're still a little iffy on it, maybe drawing a picture will help you. Here are 2 points, and it says they're 60 miles apart. Now, one cyclist hits that point, and then they start moving towards the center. The other cyclist hits that point, and he starts moving towards the center. Eventually, they're going to meet. Now, if the black one is faster, well, let me ask this question. Are they going to meet in the middle? Will they meet halfway in the middle? No, because the faster cyclist is going to go a further distance. And so they're going to meet something like this. I think I want to go a little further. Okay, so they're not meeting in the middle. The distance of the fast one made him go further than the slow one. So what we know is the distances are different. Distance of the slow guy and the distance of the fast guy. Okay, what about the times? It says, hey, they meet 2 hours later. So, I'm going to call the fast one, according to the sentence, the 1. And the slower one is the other. So I can translate word for word from English to algebra. Now, if you need to go fast and slow, that's okay, as long as you're clear which one is fast and slow and which one has the formula for speed. We'll illustrate that in a moment. Okay, what we've learned is this distance is different than that distance. We can see it in the drawing. They don't meet in the middle. The faster one went a further distance. Now we also know the speeds are different. There's a fast speed and a slow speed. If we just leave it alone right now, we got 4 unknowns. That's not good. Next question about time. How long was the fast guy riding his bike? Well, it says they met for 2 hours later. So the fast guy was riding his bike for 2 hours. How long was the slower cyclist riding? Well, he also was riding for 2 hours. Their times are the same. Because once they got to this distance of 60 miles apart, they both rode for 2 hours, and eventually they met in the middle. Okay, so that's helped us with the chart. But now the speeds, that's a problem. I'm going to come back and talk about distance later. We have a fast speed and a slow speed, and we do not want 2 unknown variables. We want to pick one variable for both. Now, what should be the speed for the unknown? Well, the faster guy, his speed is depending on the slower guy's speed. There's a formula for the fast guy's speed. It's, if we call the dependent one, this guy here, his speed is r, then we can put r right here. And the fast guy is 1.5 times r. So if the slower guy's speed is r, then the fast guy is 1.5 times r. So this makes it so that I have only one unknown. Trying to get rid of that extra period there. I only have an unknown variable r. So the unknown variable r is the speed for the slow guy. And there's a formula for the speed of the fast guy, 1.5 times r. Okay, so this problem actually had those two unknowns, and I used the variable for the other to be the slow speed, and 1.5 times slow speed to get the fast speed. Now, if you did that backwards, you would get your equation backwards. If you put the 1.5 r for the slow guy and r for the fast guy, that would have your interpretation and your final answer backwards. It would be all messed up. So that's why you got to be careful and think about the meaning of every piece. Okay, now I'm supposed to find the speed of the faster guy. We'll come back to that later, but I got to find the speed. Okay, so, but I can't find speed until I get an algebra equation. Now, in the last problem we did, the cop overtook the runner on his bicycle. He overtook the runner, so their distances were the same. In this case, it's not the same distances. We can see them, but there is an equation here. There's a total of 60 miles. So the distance of the one plus the distance of the other has to add up to 60. There is an equation. I did a verbal model. And so if I can figure out a formula for the distance of the one, well, distance equals rate times time. So if I take rate times time here, that's rate 1.5 r times the time of 2 plus the distance of the other guy. I'm going to change colors for that. Distance equals rate times time. So this guy here, if I take rate times time, I'm going to find his distance, which is rate times time. And this all adds up to 60. The two cyclists' distance total 60. There's the equation. And with that equation now, I can start solving. I'm going to simplify the equation first. I have 1.5 times r times 2. Well, you don't have to write this down, but it's like 2 times 1.5 times r. I'm using the commutative law and putting it in order. 2 times 1.5 is 3r. And r times 2 is the same as 2r. Now I have two like terms, 2r terms, 3r and 2r is 5r equals 60. I'm going to divide by 5. Now the algebra is going really fast. It's the translating that takes the thinking. And we get r equals 12. Okay, now if you stopped here, you would not be correct. This algebra is perfect. The equations are perfect. The answer is 12, but if you stopped here, it's not the correct answer. And it goes back to the meaning. What does R mean? Well, R means 12 miles per hour, but it is for the other guy. The other guy is the slower cyclist. We haven't answered the question yet. The faster guy equals 1.5 times the r, 1.5 times the 12, which is going to equal 18 miles per hour. There's the final answer. Okay, so we looked at a new tool here. Consider using a chart when you're using these distance, rate, time problems. Keep studying on this. They take practice, but the more you practice, the better you get. All right, study hard. I'll see you later. Bye-bye.